right, finish this up last class. Your slideshow says, make sure you do the worksheet. You were doing the worksheet when we left last class. Remember, the talking points are located in that other packet that you received in case you want to add some stuff to that. But we are now recording so we can get intermolecular forces and phase diagrams complete for our classes. The first thing we need to talk about is vapor pressure. All right, at any temperature, some molecules in a liquid have enough energy to escape. What is it called when they do that? You have the notes. Don't act like you don't have them. Not sublimation.
Vaporization.
No.
Generally excited.
Evaporation.
Wow. Why was that not labeled?
All right. Evaporation. So, if I was to put a glass outside today with 3/4 of the way full, and I also had another glass, that same glass, and I put it outside in the summer, and I put a lid on it, what would happen to the lid today versus the lid in the summer? A little bit of bubble in the summer, right? It would give a little bit of a give. That's vapor pressure, right? Is it boiling? No, it's evaporating, creating vapor pressure on the top. That's what we're talking about. So at a higher temperature, all right, what happens here? What's going to happen? I'm way off. So as the temperature rises, the fraction of molecules that have enough energy, God bless you, to escape increases. All right, so at a higher temperature, it's going to escape. It was great today. We have Cosette Riley in first period. She's like, I walked into my car this morning and I looked down and I had a cup and it was liquid water and I shook it and it all became ice. It's perfect for our discussion today. All right, it's perfect. So think about that. Think about that for a minute. Think about that. We're going to get to that in a minute. So as you noted, in the summer you're going to have more vapor pressure. Molecules that come off the top of the liquid have enough energy, sufficient energy to break what? To break what? What are they breaking?
Bonds.
Intermolecular bonds.
Intramolecular?
Inter.
So that brings me to my QOD. And I can't really write on this.
Question of the day.
Difference. Oh my lord.
Why don't you use an expo marker and erase it?
Between intra and inter molecular forces. So, what do you think?
Inter is one between like two atoms together, and one between like big groups of atoms bonding together.
Yes, because you were in the discussion with me yesterday. All right? That is correct, Julie. All right? Inter is between molecules or between atoms of the same. All right? Intra is inside. What holds together the specific molecule? So you cannot have ionic bonding and hydrogen bonding. Ionic is what holding the molecule together. What's holding together the trillions and quadrillions of molecules together in the liquid. Because if they weren't held together, they just go off into their own space and we wouldn't have water, we wouldn't have liquid, we wouldn't have anything. All right? So what is holding those together are the intermolecular forces. So don't get confused by that. If something naturally has a charge to it, sulfate, permanganate, ammonium, carbonate, those, no matter what, are held together, the molecules held together by ionic. But the intermolecular forces could be hydrogen or dipole-dipole. Or they could even be dispersion. Right? How do we know the difference between the three?
Polar, non-polar.
Polar or non-polar? If it's non-polar, it only has what? London dispersion, intermolecular forces. If it is polar and doesn't contain hydrogen, it has what? Dipole-dipole. Or it's H-NOF. 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 What's H-NOF? Hydrogen combined with nitrogen, oxygen or fluorine, hydrogen bonding. If that doesn't make sense, I can't do anything else for you. All right? That's it. We'll talk about covalent network solids in a minute. All right, vapor pressure. So again, my favorite questions involving stopcocks. All right, here we go. We have stopcocks in here. All right. So all those stopcocks you can open and let the gas out. You can let it in, let it escape, whatever you want to do. That controls the amount of gas. It was in your question of the day today on email. If you saw the question of the day, you would have seen the question referring to the stopcock. Now, on that, all right, you should know that we're always doing pressure and volume, pressure 1, volume 1, pressure 2, volume 2. Anything according to a stopcock is a P1, V1 equals P2, V2. Okay? Just a side note. So if you're trying to answer that other question, the total volume is when the stopcock is open, how much total volume is in the system? Those of you that did test corrections for the second test or fourth test, whatever it was, you now understand that. All right, so in here we have liquid ethanol. That is a volatile liquid. What does that mean? It's volatile. If I opened up ethanol right in this room and I popped the cap off of it, what would happen?
Flames.
No. You would what?
It would evaporate.
Okay. Well, you would smell it. All right, you would smell it. So what does that mean? That these molecules have sufficient energy, more energy than of water or something else that you're not really smelling, to go ahead and fill this container. So when you open it up, as the molecules escape the liquid, the pressure on their pressure increases. So this is going to go up. All right, this is a simple manometer. All right, not a big deal. And then we have the liquid and vapor reach a state of dynamic equilibrium. Liquid molecules evaporate and vapor molecules condense at the same rate. Equilibrium, same rate. All right, that's what we're going into. Reaction kinetics and equilibrium before Christmas. New stuff. All right, not completely new, but equilibrium will be new for most of you. Okay, so we're going to be calculating that stuff here in the future. So, but you need to know equilibrium is always trying to get to the place of least resistance. It's going to be nice and nice and nice for you. All right, vapor pressure. The boiling point. Now, this is a discussion I had with students yesterday. AP students. The boiling point of a liquid is the temperature at which the vapor pressure equals atmospheric pressure. If you didn't know that, isn't that very handy in some of the calculations you may need to do? All you have to do is find out what atmospheric pressure is. In this case, what are we saying the atmospheric pressure is?
Standard.
Standard pressure. Which number up there represents standard pressure?
760.
760. All right, so this guy right there, 760. All right, standard.
So hard. That's a B.
So hard to do this. All right, standard pressure. So we got, 1 ATM. We may have 760 torr. We may have 1,130 millibars. I don't know. 101,325 pascals. 29.92 inches of mercury. Something like that. That's on your news. All right. So that could be anything. But when that line hits standard pressure, where that line intersects is your boiling point. So, with that being said, let's take a look at these three substances. We have dimethyl ether, ethanol, and water. If you didn't know anything about those three things, what could you tell me is controlling, and ethylene glycol, we have this here too. I didn't even, little guy stuck under the rug there. All right, little guy, ethylene glycol. What could you tell me is control, what do you think, which one's going to boil the fastest? Diethyl ether?
Yeah.
Okay, why? All right, what else?
Steepest curve.
All right, the slope. All right, so the slope, the steepest curve. all those wonderful things is going to boil quickly. If we didn't know what these were, and I wanted you to hypothesize, let's just do those three. Why do you think that the curves are different? This has a bigger slope, this has a nice curve, this has a longer curve. Why do you think?
Intermolecular forces.
Aha! So this is controlled by intermolecular forces. All right, now to see if we know what we are talking about in our homework, all right, what would be the red, orange, and blue? Which forces would be the red, orange, and blue? You took them all, yeah.
London, and dipole, and hydrogen.
All right, dispersion, dipole for the orange, and then H bonding. All right, H bonding. Sorry about that. It's just a nice little review. But we do know that water does have hydrogen bonding, but we also know that all alcohols, so this ethanol here, that has hydrogen bonding too. All alcohols have hydrogen bonding. All right, all alcohols have hydrogen bonding. All linear hydrocarbons, what are we going to have in a hydrocarbon? All CH things with just C and H. What are we going to have?
Dipoles.
Just CH.
Dipoles.
Not hydrogen bonding. What do you think?
Dipole.
We got dipole going out there. Let me take a look. 2.5 and 2.1. What's the difference? So they're always going to be nonpolar, and they're going to be dispersion.
That's all.
All hydrocarbons. Anything with C and H. You can have C25, H55. It's just going to be dispersion. It doesn't matter. All right? That's a huge thing. Kind of gather up. If I have an alcohol, hydrogen bonding. If I have a hydrocarbon, dispersion forces. It's going to be nonpolar. Okay? Something for you to think about. The normal boiling point is the temperature at which the vapor pressure is 760 torr, like I said, 29.92, whatever that may be. All right, you have your notes?
No.
Oh, the big packet? Oh, sorry, I don't have another one. I'm sorry. Okay, it'll also be on mine. All right, phase diagrams display the state of a substance at various pressures and temperatures in the place where equilibrium or equilibria exists between phases. You have to know every single stinking thing on this. We're going to practice it today. Those are the sheets you picked up today. All right, solid, liquid, gas, solid, liquid, gas. All right, sublimation, deposition. What's the difference between sublimation and deposition?
Something going from a solid to a gas and vice versa.
Which one?
Well, sublimation is going to a gas, deposition is going to a solid.
Solid to going from a gas to a solid? Yes, okay. Condensation, vaporization, melting, and freezing. We're also going to talk about each one of these points. We need to know all about these points. All right, and guess what? Then from data, I gave you an old AP question. Just because I don't want you to think you never practiced it before you saw it on Friday. We're going to actually draw one from data. Okay? Not hard. The AB line is the liquid vapor interface. It starts at the triple point A, the point at which all three states are in equilibrium. So, let's just say I was here, right here. All right, and I increase pressure. All right, what would happen? What phase would it become? Solid. All right, increased pressure became solid. If I went here and I increased temperature, it become a what? All right, if I increase temperature and pressure, right? You understand what I'm doing?
Yeah.
Okay, have you seen these before?
No.
Okay, all right, that's fine. All right, so this line right here is A to B, liquid vapor interface. It ends at the critical point B, and the critical, above this critical temperature and critical pressure from the liquid and vapor are indistinguishable from each other. So at that point, when the pressure is so high and the temperature is so high, it can be a gas or a liquid at any moment in time. It can just switch. Kind of like Cosette's car today. It was a liquid, and then she gave it a little energy, and guess what happened? Froze. Right? It was 17 when I walked my dog. So it does make sense. A little bit of energy. If everything is static and nothing changes it, most of the time it's going to probably stay at that phase. All right? When you just jostle something a little bit, or it's the same thing as the exploding water cup. We've all done that before, of course. The exploding water.
Oh, we do that.
You take a cup of water, you put it into a microwave, take it off the oscillating plate, put it in there 5 minutes, and then literally if you jostle the microwave, it blows up.
Never gone up a microwave.
I gotta see this.
Can we do that?
Check it out later.
No.
Check it out later. We'll check it out. All right, so it ends at that. Each point along this line is the boiling point of the substance at that pressure. So how do you figure out what it is? It's very simple. Now this is going to be hard for me to do. So the question says it's at 77.1 atm pressure. What is boiling point? All right, so I don't know what this scale is. I'm just making up this scale. I'm going to say like 1 is here and 7 is here. Let's just say whatever, right? So what I'm going to have to do to figure out the boiling point is go from here, draw a straight line over to this line, and then go down. And whatever temperature, whatever temperature that actually hits is going to be the boiling point. That's how you use that graph. It's pretty easy, right? And now my line's all messed up because of the pen. If I had a pen, I mean, literally, if I had a pen that would work, I could probably do the perfect circle, no problem. You know, something like that. But the pen's a little bit off. That's a pretty good circle, isn't it? Like that.
There's a big
All
gas
right?
on it.
Well, I mean, you know, it's a pen, not me. All right, so you go over that line, you figure out what it is. All right, if I wanted to do melting point at 6.1, if I wanted to do melting point there, I'd go from this line over to here and then down. All right, that's how you use it. All right? I don't know. All right, but that's how you use this graph. All right. The AD line, not the attention deficit disorder line, but the AD line is the interface between liquid and solid. All right, the melting point at each pressure can be found along this line. All right, very simple. So the melting point at each pressure can be found along this line. We just showed you how to do that. All right, if you had a temperature of like 73, and I wanted to find out what, if I went here, I could go back and find out the pressure too. Or you can go backwards too, right? Don't forget you can go backwards. All right. Below A, the substance cannot exist in a liquid state. Below A, it cannot be a liquid. All right, can never be a liquid below A. All right, A is the triple point where all three phases are existing at one time. Just like the water in the car. It was existing at one point. All right. Note the high critical temperature and critical pressure. This is of water. All right, so they're all going to be different. They all do not look the same. These are due to strong van der Waals forces between the water molecules. What are the forces? We know it more specific than that. Hydrogen, dipole, and dispersion. It has all three. So when you say it has all three, you use this term. If it has all three, you use this term. That's the designation. That's the difference. So if it has all three, use that. If it only has dipole, and on the dispersion, you just say those two. All right? But if it has all three, you say van der Waals. All right, so it's a little bit different graph. It shows you what's going to happen at D. What's D?
The critical.
Critical point. What happens above D?
You can't.
Can't distinguish between gas and liquid. So you notice it's kind of miscolored, like yellow and blue at that point. Okay? All right, the slope of the solid liquid line is negative. This means as the pressure is increased in the temperature, at a temperature just below the melting point, water goes from a solid to a liquid. All right, slope is negative. All right, which line are we talking about here? Which line? Am I here? Am I here?
Here.
Or am I here?
The second one.
Second one.
Here?
No. That one.
Yeah?
Yeah.
Yeah.
Eh?
No.
No.
Aha, good. Okay, you want to make sure you know what we're talking about. You know. All right, carbon dioxide looks a lot different. What can you tell me about the slope of that line that we just looked at for water?
Has a,
Positive slope. So that makes a huge difference. Somebody correlate to me the last slide with this slide and that line before I talk about this one. Go ahead.
It means that unlike water, which is more dense as a liquid, which is more dense as a liquid, carbon dioxide is more dense as a solid.
Yeah, exactly. All right. Carbon dioxide cannot exist in a liquid state at pressures below 5.11 atm. Carbon dioxide sublimes at normal pressures. Is 5.11 atm a large pressure or little pressure?
large pressure.
That would squash you.
It's ruin your day kind of pressure.
That would ruin your day. That's like, I'm going to put you at the bottom of the ocean without a suit on. Good luck. That's what we're talking about. Crush you. I will crush you. All right. The low critical temperature and critical pressure for carbon dioxide make it supercritical carbon dioxide for a good solvent for extracting nonpolar substances such as caffeine. Let's think about that. What am I trying to say in this? Okay, give me a couple things. What do you think one thing I'm trying to say is? What do you know about extracting nonpolars? Yes.
Well, it would mean that supercritical CO2 is nonpolar, right?
It means that we know that carbon dioxide is nonpolar. It's definitely nonpolar. It only has dispersion forces. So what is caffeine? Caffeine is,
Nonpolar.
and what happens to what?
Lights.
Lights, dissolve lights. So why is this important? For you, you are teenagers. This should make a big deal to you, especially at parties or, you know, when you have pizza or chips. Why is this important? Tie them together. All right, hold on. Ready? I'm going to do charades. Soda! That's why this is important. What do they pump into soda? Carbon dioxide in order to dissolve the caffeine. Right? Because water is what? Caffeine is. So if you mix the two, what would happen? It'd be two different layers. So in order for get the caffeine dissolved, they have to pump it in with carbon dioxide so you can get all amped up for the big party and the dance. Yeah.
Wait, so is that why people drink like flat Coke when they do like sporting events? Because like if there's no CO2 in it, then you get the caffeine more directly, or
That just sounds disgusting.
I don't know.
I've never heard
Marathoners will leave their Cokes open the night before and like drink flat Coke.
Wow.
Maybe. I would just go 5 hour energy.
I just wouldn't run a marathon.
Something like that. I just probably do Red Bull.
I'm not speaking from experience.
All right.
Just bike straight up to
Yeah. Not really.
not legally.
Yeah. Okay. Because caffeine has 0.25 milligrams of non-dissolved caffeine will kill you.
Oh, good.
0.25 milligrams. We can think of solids falling into two groups. Crystalline, particles that are highly ordered in arrangement. I'm going to touch on this. Basically, all you need to know is unit cell. Then I'm going to hit covalent, network covalence. You do not need to know that, but this is really going to be like a 2-minute vignette. The other thing we spent about, I don't even know when we started, 20-25 minutes, phase diagrams and the worksheets. Way more important than this. All right, and I know you read it, so you do have some little bit of background. You outlined it, but I'm not going to go into more than that. Amorphous, no particular order in the arrangement of particles. Does anybody know anything that's amorphous? Glass. Glass and an amorphous solid. If you go to a church that has really old windows, the bottom of the glass is way thicker than the top of the glass. It just keeps moving very, very slowly down that. All right, an amorphous solid. I always like to think of amorphous solid too as kind of a really dense salad dressing. I kind of think of an amorphous solid, or a silicone breast implant, one or the other. I mean, I don't know. Okay. I mean, one or the other. Those are the two things that I think of. All right. In ionic crystals, ions pack themselves such to maximize attractions between the repulsions between the ions. All right. So closely packed layer of spheres, layer AB, positive, negatives, positive, negative, however that may be. For that, we're just going to minimize it.
Hello, attendance, please.
All right. Crystalline solid. Because of the order in a crystal, we can focus on a repeating pattern called a unit cell. Definitely have to know the definition of a unit cell. But after that, I wanted to expose you to those three: primitive cubic, body center cubic, and face center cubic. Very simply put, is that a primitive cubic is just going to have sheets. All right. A body center is going to have an atom in the middle. Nothing on the edges, nothing on the outside, just on the corners. And then a phase center is going to have atoms in the middle and surrounded by atoms all outside. Okay? Yeah, right. But I'm just exposing that's basically so rare, asked on AP, like one every 20 years, something about that. So that's it. I'm done with that part. This is what they look like. You'll never have to calculate it, so don't worry about the 1/8 or anything like that. There are several types of arrangements in crystals, such as the one shown above. There's with a primitive cubic. There's with the body centered face. So it just shows a face at each center, each part of the cube. I mean, I would love it if you saw a picture, you could identify it. I think it'd be very rare that it would happen. Determine the empirical formula of many ions. Each element fall within the unit cell. Don't worry about that. All right. This, if I got this question, all right, if I got this question, for me, it would be very simple. All I would do is look at the periodic table. I would say chlorine's a -1, cesium's a +1. What's the empirical formula? If this is a -1, this is a +1.
Oh.
Right? And so they're like, oh, determine it from the picture. Well, you're given that thing. So -2, +2.
Oh, it's right. It's cation ion, right?
All right. +2, -1. Right? Okay. I wouldn't ever have to worry about looking at this, determining a formula. One, they don't print it in color. So they can't, there's no way that they could do it. Right? So that's all. All right. I don't know, I have a couple left. I want to try to get through it. This chart is all multiple choice, all the time questions. All right? You've gotten some of this stuff, whatever. You got to keep ingraining it in your mind. This is a Quizlet type of sheet. All right? And why is it a Quizlet? And the most important part of Quizlet part is the examples. All right? The examples are huge. Properties are, semi-huge. Obviously, yes. And I'm not worried about that. And then this. Focus on this one. All right? And then also say that we know that this is delocalized electrons. That's what controls this. All right? Delocalized electrons. All right? So covalent networks is how we're finishing. Very hard, very high melting point. Poor thermal and electrical conduction. Examples: diamond, carbon, like coal, charcoal, carbon like graphite, quartz, silicon dioxide, covalent networks. You need to know those. Another one would be something combined with C. All right, WC, a covalent network solid. All right, so stuff that are kind of attached to C, 90% chance that they're going to be a covalent network solid. All right, these are the two. What are we looking at? anytime that you should see a group 4 element, a group 4, carbon or Si, red flag should go off that that's going to be some type of covalent network south, 90% of the time. Carbon or silicon. Okay? That's my ring, ring, ring. Here we go. All right, diamonds are an example of covalent network solid in which the atoms are covalently bonded to each other. Nice, tightly packed. Why do you think they're more tightly packed than the graphite?
High pressure.
Where are they found?
In the ground.
Deep underground. Where would graphite be found?
Not.
Near the top, near the surface of the earth. All right, so they're found under pressure. The weight of the earth packs in this, and then graphite is this. They're just in sheets. They're not formed under high pressure, so they're much easier to hold together, and they're held together with van der Waals forces. What does that mean? All three. They tend to be softer and have lower melting points. All right. Okay. So the other one was harder and higher melting points and softer. Did I leave that up? I'm sorry. I might have went through that too fast. Metallic solids, of course. In metals, valence electrons have delocalized electrons. Nobody believed me. They had to wait till I put up the slide. I kept saying it the whole time. All right, so metallic, silver, gold, frankincense, myrrh. Yeah, so these electrons, they flow, they move throughout. All right, by them moving, they keep everything attracted and attached to each other. They're not van der Waals forces. They're not covalent. They're not ionic. They're metallic solids. So any metal, that's what gives the ability to be ductile, conduct electricity, malleable, all those wonderful things. The moving electrons are what electricity is. And that is it.